Hello everyone, I'm Chen, a PhD student at UT Austin, and today I'll be presenting our work, SoundSpaces 2.0, a simulation platform for visual-acoustic learning. Human perception is a multisensory experience. As humans, we interact with the world by seeing, hearing, touching, and smelling. Among them, vision and sound are two of the most important modalities, which provide complementary information of each other. For example, at the object level, the appearance of an instrument indicates the sound that it produces, while at the environment level, the scene geometry and the sound emitter location affect the acoustics of the sound. To study the acoustic correspondence between the visual and sound, taking the complete physical measurement of the room is not feasible, and thus we introduced SoundSpaces 2 years ago to simulate how sound propagates in space from the emitter to the receiver with room impulse responses, and provides pre-rendered IRs for pairs of discrete points in replica and Matterport 3D datasets. However, these renderings are not configurable, continuous, or generalizable. While SoundSpaces has been widely used for various research, it was unclear how realistic the acoustic simulation is and how well trained machine learning models generalize to real data. In this work, our contributions are first to release SoundSpaces 2.0 that is continuous, configurable, and generalizable, and secondly, we validate the performance of the simulation with real acoustic measurements. We also prepare a large-scale panel IR dataset for visual acoustic learning research, and lastly, we benchmark continuous audiovisual navigation and far-field ASR and show sim to real for the latter. Here, we briefly illustrate the simulation pipeline.
Dinner's ready! Dinner's ready!
SoundSpaces 2.0 offers both spatial and acoustic continuity, and here is one example. Users can also change all these parameters, including the simulation parameters, the microphone types, and also material properties for various objects. SoundSpaces 2 supports arbitrary scene datasets, including Gibson, Matterport 3D, Replica, HM3D, or even in a wild mesh scale dataset like Eagle 4D or your own environment. We offer two rendering modes. The first one is high-quality mode for perception-only visual acoustic research, and the second one is high-speed mode for embodied AI research. We show that high-speed mode achieves 8 times speed-up with a small sacrifice in accuracy. To validate the simulation with real IRs, we collect acoustic measurements of the apartment in replica dataset and compare to IRs rendered in SoundSpaces 2.0. And in the plots below, we show that SoundSpaces 2.0 has a better match of direct-to-revolution ratio with real compared to SoundSpaces 1. To prepare a ready-to-use dataset for visual acoustic research, we pre-compute and release the largest ever image IR dataset in the format of panorama, IR, and polar coordinates, and below is one example. The first task we benchmark is continuous audiovisual navigation, where a robot is tasked to find a sounding object in an unknown environment. The robot can move continuously in the environment. Collisions with objects or walls is possible, and acoustic rendering is both spatially and temporally continuous. We train and test distributed audiovisual navigation policy, and we compare with the same model trained on a discrete setup and test it on a continuous setup. We show that lack of acoustic continuity hurts generalization more than the lack of spatial continuity, and training in a continuous environment leads to the best generalization. Synthetic IRs are often used for data augmentation for far-field ASR, and we fine-tune sold-out ASR models on IRs generated from various systems, and we test them on real data collected in daily environments such as home and meeting rooms. We show that model trained on SoundSpaces 2 has lowest error rate on real data. For more information, please visit our project page and GitHub repo. Thank you.